So atomic number and mass number, isotopes and isobars. In the in the previous chapter, we had spoken about mass, atomic mass, and the molecular mass. So that concept is different from what we are going to be studying now. There we had spoken exclusively in terms of the mass of that particular substance. Here, mass number is completely different from the atomic mass. So let's start. Atomic number. So atom, as we know, is electrically neutral. So we got to know that the number of protons are equal to the number of electrons. So basically, the number of protons in a particular atom is the atomic number. Remember, despite the fact that the number of protons being equal to number of electrons, we do not consider number of electrons for atomic number because electrons can be removed when a chemical reaction takes place due to valency. All of these reasons lead to decrease in the number of electrons. I mean, if you remember in grade 9, you would have, learned about Bohr's atomic theory and how valency happens. So valency happens, valency is basically the ability of an atom to lose or gain electrons. So obviously there will be a difference in the number of electrons. However, number of protons of that particular atom stays the same under normal conditions. So number of protons equals to the atomic number. So the number of unit positive charges in the atom is its atomic number. Mass number, on the other hand, is not atomic mass, but it's the mass number. So mass number equals to the sum of number of protons and number of neutrons. So this is the general representation. Suppose X is the symbol of the element, hydrogen is H, helium is He, and so on. Mass number is A and it's represented at the top, whereas the atomic number is represented at the bottom. So this is the general representation. Remember this. So there are two in-text questions. First one, calculate the number of protons, neutrons, and electrons in this particular element. First of all, let's go back to this. Here we know A is at the top, that's the mass number. Z is the atomic number. One tip I always, try and use for understanding the difference between these two is that atomic number is always going to be less than mass number because atomic number is the sum of protons and the neutrons. So obviously the atomic number will be less than the mass number. So this is something that you can use when you have this particular representation and you do not, it doesn't, it sometimes might slip your mind and you might be confused as to which is the atomic number, which is the mass number. So the atomic number is always lesser than the mass number. So here the atomic number is 35 for bromine. So the number of protons will be equal to 35 because the atomic number equals to the number of protons. And since the number of protons equals to the number of electrons is 35. So from the atomic number, we were able to calculate the number of protons as well as the number of electrons. Now the mass number is the sum of protons as well as neutrons, basically number of protons and the number of neutrons. So we're just substituting mass number as 80, and because we know the number of protons is 35, from which we were able to calculate the number of neutrons, and the number of neutrons is 45. So for bromine, whose atomic number is 35 and mass number is 80, the number of protons and electrons are 35 and 35 each, and the number of neutrons is 45. So the next question, the number of electrons, protons, and neutrons in a species are equal to 18, 16, and 16 respectively. So 18 is the number of electrons, 16 is the number of protons, and 16 is the number of neutrons. Immediately, we know that the number of protons is not equal to the number of electrons, and you are right. So let's first look at the atomic number. So we need to assign the proper symbol. So we need to assign this general symbol for this particular element. So atomic number equals to the number of protons. So the atomic number is 16. And mass number can be calculated by the sum of protons and neutrons, and that's 32. So we know that the atomic number is 16. The mass number is 32. Now, the reason we've put -2 over here is because the number of protons is not equal to the number of electrons. So here you have 18 as the number of electrons and protons is 16, which means this particular atom has 2 extra electrons. And so that's why it's shown as a -2 charge. However, for example, this is just an example. It's not for this particular element, but for example, if I had 18 and this assume it was 16, right? So 17, 18, it was 20, right? Then automatically I would have had to write +2 instead of -2 because your proton, there are 2 extra protons over there. So since here you have 2 extra electrons, because of that, electrons have a negative charge, so minus and 2. If it was protons, it would have been +2. Notice sulfur does not show that, but yeah, unless and until it's forming a specific bond. Anyways, so this particular rule of the number of protons not being equal to the number of electrons is not followed when the particular atom is charged or when it forms an ion. So isotopes of an element have the same number of protons, but the different number of neutrons. So basically they have the same atomic number, but a different mass number. Here we have example of protium, deuterium, and tritium. These three are isotopes of hydrogen. So the first one, protium, this is a most abundantly found element. I mean, most abundantly found isotope of hydrogen. And if you can see, it has only one proton and one electron. So its mass number is 1. Whereas here you have one neutron and one proton, which makes its mass number 2. Whereas because tritium has one proton and two neutrons, its mass number becomes 3. Notice the number of electrons does not change. So because the number of electrons do not change, these three are chemically similar to each other. They show similar chemical properties. However, its mass number is different. So isotope has the same atomic number, but it has a different mass number. Isobars, on the other hand, have the same atomic mass, or rather the same mass number, but a different number of protons. So they have the same atomic number, sorry, they have a different atomic number, but they have the same mass number. Here also it's mass number, by the way. So here, if you can see, the number of electrons are different, 18 and 19 and 20. The number of protons are also different, 18, 19, and 20 respectively. But the number of neutrons are in such a way that the total mass of these three, or rather mass number of these three elements is 40, 40, and 40. However, its atomic number is 18, 19, and 20. So these elements do not show similar chemical properties. They have only the same mass number. So with this, we finish learning about the atomic number. So atomic number equals to the number of protons. Mass number is the number of protons and plus the number of neutrons. Isotopes have the same atomic number, but different mass number. Isobars have the same mass number, but different atomic number. In the next video, we are going to be studying about the developments that led to Bohr's atomic theory. Rutherford's theory didn't hold up two important things. It did not explain the stability of the atom, and it was not able to explain the arrangement of electrons. So that led to another theory called as Bohr's theory, whose developments, that is why it happened, is what we're going to be learning about in the next video.